Welcome to Judo. If you were not expecting this call, please hang up. Otherwise, press any key on your phone to log. Thank you. Goodbye.
Hey, good morning, Dr. Banerjee.
Hey, Harry. Are you guys okay during the storm? Do you have power and water?
Yeah, I got it back about 5 days ago. So
Okay. Good.
we're back to semi-normal now. How about you?
We did not lose power except for a few hours, and we hadn't lost water either. But our next door neighbor, by mistake, shut off our water on Friday. So even though we had city water, we didn't have water for 3 days before I noticed on Sunday. Our water mains are right next to each other, so it's very confusing.
Everything's back now, so that's good.
Mm-hmm.
I just like to say hi and meet my professors because it's hard to do it this semester.
Yeah. Good morning. Let's get started. I hope you guys survived during the storm and had water and power. We lucked out. We had both, except for a brief period. If there's any issues and concerns you still have with maybe no water, power, internet, please let me know, and I can give you extensions on homework, due dates, and stuff like that. I've already extended the due date on some of the homework, and I've modified the course schedule online, so you can look at the new due dates. Okay. Now, because the due dates have been postponed, unfortunately, we'll not be able to give extensions for people who are late, because I need to be sort of on schedule. Also, in terms of the midterm, we'll only test you on stuff covered up to the midterm. And I believe that'll be only chapters 1, 2, and 3. So that's all they will be tested on. All right, so let's get started with a quick review of what we discussed before the storm. So we have been talking about crystal structure, where we have a periodic arrangement of atoms in space described by the unit cell. And then that results in a periodic array of Coulombic potentials, 1/r type potentials. And then we said that we can study the motion of electrons in this periodic crystalline potential. And these can be described quantum mechanically in terms of wave functions, which turn out to be more or less plane wave-like, but plane waves modulated by a function with the same periodicity as a crystal. Those are known as Bloch type wave functions. So essentially, you put in the periodic potential into the Schrodinger equation, and you crank the machinery, and out pops the eigen functions and the eigen energies, which are the allowed energies in the crystal. Okay. Now, the study of quantum mechanics teaches us that everything in nature has a wave-particle duality captured by these two equations. Energy equals h nu, or h bar, which is h over 2 pi times omega. Omega is frequency in radians per second, so it's 2 pi times frequency. The other equation in quantum mechanics that's also always true is that the momentum is given by h over the de Broglie wavelength, or you can write that also as h bar k, where k is a wave vector equal to 2 pi over the de Broglie wavelength. Now, notice, of course, that these two expressions capture the wave-particle duality very well, because things like frequency have connotations of a wave. Energy, you could have it for energy of a wave or a particle, but generally we can think of energy as being a particle-like concept. Momentum is clearly a particle-type concept, while wavelength, or k, which is known as a wave number, is clearly a wave-type concept. Like I said, these two expressions are going to be true for everything that we study, for electrons, photons, whatever. Okay. However, you can also sometimes be interested in a relationship between quantities like this, energy and momentum being a classic example. And those relationships will depend on whether I'm looking at an electron or a photon or whatever. In the case of electron, we saw that you can write the energy as a function of k as a sum total of the kinetic plus potential energy. Kinetic energy is equal to p squared over 2m, and plugging in p equal to h bar k, you get equal to h bar squared k squared over 2m, the mass of the electron, except that we saw that the mass is modified when the electron moves in the periodic crystalline potential. Okay, so these complicated interactions of the electron with this periodic array of atoms in the crystal are summarized by a single number, the effective mass, which I call m star. So once I've done that, once I've solved the Schrodinger equation in the periodic crystalline potential to calculate the energies as a function of k, or equivalently in terms of this effective mass, I can now forget about the periodic crystalline potential, and you can think of plane waves propagating in the crystal, but with a modified effective mass. So then what you have to do is you only have to worry about the external forces that you apply. What are the external forces? So this could be due to, for example, a battery that you hook up to a transistor, giving rise to electric field. The electric field will impose a force, which is the charge of the electron times the electric field. So that's all that you have to worry about from now on. And clearly that's a huge simplification, because if I give you a problem involving a diode or a transistor where I apply voltages, you certainly don't want to have to solve the Schrodinger equation for the periodic silicon crystal every single time, right? I mean, that's a tough way of doing problems. What we studied in chapter 3 then was, if you look at these energies, one finds that according to quantum mechanics, you cannot have all possible energies in a periodic crystalline potential. You're allowed a so-called band of energies in the conduction band. You're allowed a band of allowed energies in the valence band. They have a finite width of allowed energies, but then you have forbidden energy states in what's known as an energy band gap, okay? And that's the most important concept in semiconductor physics. So you have allowed bands of energy, conduction and valence band, but nothing allowed in the middle, the energy gap, provided, of course, I have a defect-free crystal, all right? Now, of course, we studied that below the valence band, you have other gaps and other allowed bands and so on and so forth. Similarly, above the conduction band, you have other gaps and so on and so forth. But for semiconductor physics purposes, all that you need to worry about is the highest, almost completely occupied band, which is known as the valence band. And these evolve from the electrons in the valence shell of the atom, in this case, silicon, say. And then the next highest excited state, which then leads to the conduction band. And what one finds, we saw, is that the valence band is full of electrons, but not completely full at finite temperatures, because a few of these electrons in the valence band can be excited across the energy gap into the conduction band, and this gives rise to these negatively charged conduction electrons moving with an effective mass m star, and what's left behind are these positively charged missing states, which we call holes, okay? Now, on the right-hand side, if you just focus on the right-hand side, where I'm showing that the bands as being flat, that's the simplest case. Let's see what the axes are, okay? So we saw that the x-axis corresponds to the position in the semiconductor device, while the vertical axis increasing upward corresponds to electron energies increasing upwards. Now, what part of the electron energy am I plotting? Well, if I'm at the band minimum, say at EC, I only have potential energy, which is written as a V of R, because the potential energy in general can be a function of R, or in 1D, it's just going to be a function of X, okay? But then you add the kinetic energy, P squared over 2M, or H bar squared K over 2M. So as I add kinetic energy, I go up in the band. Conversely, we saw that for the holes, if I'm at EV, the valence band maxima, I only have hole potential energy. But then if I add kinetic energy to the hole, I move downwards. So the axis, the energy axis of the holes is downward, while that for the electrons is upward. So once again, these are known as simplified band diagrams. And this is essentially what we'll be using throughout this course to study all devices. As I told you, you need to be very comfortable with reading these diagrams, okay? Now in this picture, I'm looking at a more complicated scenario where the potential energy, as you can see, is varying. So it's constant in this region. Now this V of R, the potential energy, is given by the charge, in the case of the electron, that's minus Q, times the voltage V. So don't confuse this V, which is shown in italics, with the potential energy, capital V of R. Okay, so minus Q times V for electrons is the potential energy of the electrons. All right. So in this part on the right-hand side, I see that the potential energy is constant. That means that V, the electrostatic potential or voltage, is also constant. And since we know that electric field E is given by minus dV dx, V is the voltage. If V of R is constant, that means voltage is constant. And if I take the derivative of a constant, I get 0. So in this region, electric field over here equals 0. Similarly, over here, electric field is 0. But in between these two locations, you see that clearly the potential energy is varying with position. Okay, so that then tells you that I have a variation of the electrostatic potential. And if I take the gradient of that, I'll get an electric field. Now, can anyone tell me between these two locations, is my electric field constant or is it varying?
Constant.
Very good, because it's
Yeah,
got
it's
a
a consistent change.
Yeah, right. On the other hand, if the electric field itself was varying, instead of this being a straight line, you'd find band diagrams like, you'd have a curve and so on and so forth, okay? And we'll see that once you start looking at devices such as p-n junctions. And then at each location, you can take the gradient, and from the gradient, you can infer what the electric field is, okay? So in this case, if I take the gradient of the electric field, the gradient of the electrostatic potential, you can write that in terms of the potential energy, and that will work out to 1 over q d. Sorry, let me over here. This will work out to 1 over q, the charge of the electron, dv dx. This v is the potential energy. The v with italics is the voltage. Okay, so if you work out the signs, you'll find that in this particular case, the electric field points in this direction. It's a constant electric field. Okay. Now let's see what would happen to an electron at a location A. Can anyone tell me what the kinetic energy of that electron is at A?
Is 0 because it's right at the edge of the conduction band?
Excellent. Can also anyone tell me if the electron is seeing a force, or is the force on the electron 0? At location A.
Would it be 0 because force is mass times acceleration? Well, actually, I'm not sure.
Well, force of the electron is equal to charge. Force would be charge, which is minus q in the case of electrons, times electric field, right? So at A, the electric field is 0 or non-zero?
It's non-zero, so
Non-zero.
it experiences a force.
Force is going to be non-zero, right? Which way does the force point? Well, because electrons have a negative charge, if the electric field we see is pointing to the right, force has to be in the opposite direction, right? So I see electron initially at A. I accelerate it in this direction because there's a force on it and it moves. Now suppose it's moved to this location. At that point, is the kinetic energy 0 or non-zero?
Non-zero.
Non-zero, because it's moved away from the band edge. Now, where did you get this kinetic energy from? I mean, you can't create or destroy energy. Where did that kinetic energy come from? Any guesses?
Isn't it, I guess, technically going like down since it's going to the left on the graph?
It's going to
So
the
it's a
left.
Potential
Right.
and getting kinetic.
Right. So it's gaining this kinetic energy from the potential energy of the battery, for example, right? I've hooked up a battery, say, between these two locations, okay? And that creates this electric field. So the electron is accelerating and gaining kinetic energy from the energy of the battery, okay? So yeah, I'm converting potential energy into kinetic energy. You can also think of it as an analog of, rolling a marble down the hill. And as it rolls down the hill, it speeds up more and more, right? So the marble gains kinetic energy from the gravitational potential energy. So in this case, the electron is gaining kinetic energy from the electrostatic potential energy, all right? Now, as it gains more and more kinetic energy, it's called a hot electron. So if it gains a lot of kinetic energy, those are called hot electrons. Now, it turns out if the crystal was a perfect defect-free crystal, this electron would keep gaining kinetic energy. But in practice, that doesn't happen. We'll see, not today, but next week, that in a practical situation, crystals will always have some defects, which will cause what are called collisions or scattering of the electron. So in practice, what will happen is the electron will gain some kinetic energy and then bump into a defect, for example, lose part or all of its energy, gain some energy, lose energy, and so on and so forth. Okay, we'll discuss those details later on when you look at electron transport physics. Okay, now how about for holes? Suppose I'm looking at a hole at this location. With electric field pointing to the right, which way is the force on the electron, or on the hole, to the right or to the left?
Right.
Right.
Right, same direction.
Exactly, very good. So once again, at this point, the hole has zero kinetic energy. It's got a force to the right. At this point, is the kinetic energy zero or non-zero?
Non-zero.
Non-zero. And where did you gain the kinetic energy from? Once again, from the battery or the electric field. Okay, and it's becoming a hot hole. You can bump into some defect, lose. Here I'm showing it loses all of its energy. It doesn't have to lose all its energy. Maybe it loses part of its energy, accelerates more, loses part of its energy, and so on and so forth. Okay. Now, on top of this simplified band diagram, which once again are plots of electron energy pointing upwards as a function of position x, I've superimposed another type of diagram, which is called band structures, which also I had discussed before the break. But here the axes are different. Here the axis is electron energy increasing upwards, same as for the simplified band diagram. But the horizontal axis is no longer position x or r, but it's momentum k. It's k. It's k is basically proportional to the momentum of the particle. Okay. Now let's see what the graphs would look like. Well, if I plot E as a function of momentum, or basically k is proportional to the momentum of the velocity, what does this curve E of k look like in this case? Well, y equal to x squared is the equation of a
Parabola.
Yeah. So this is a parabolic band structure. Now that's an approximation. We'll see in just a second. Okay. So if I plot E as a function of k, I get a parabolic shape, and these are called parabolic band structures. So once again, mind you that the vertical scales, vertical axes are the same in both the band structures and the simplified band diagrams, but I'm superimposing different horizontal scales. Okay. Position in the case of the band diagrams, but k, which is basically proportional to momentum or velocity, in the EK band structures. Now, superimposing them gives you a lot of insight. Okay? So let's once again go back to the electron at location A. It has zero kinetic energy, you guys said correctly. Okay. So in the EK diagram, what would be the value of momentum k, or wave vector k rather? Momentum is h bar k. K would also have to be equal to 0, right? Because it's got zero kinetic energy, and therefore zero value of k. All right. Now let's see, I move the electron from A, and suppose there is no scattering, it's a perfect crystal. It's moved to location B. How much kinetic energy did I gain? That much kinetic energy, right? Because the electron is that far above the band edge at this point. Now, what is the corresponding value of the k value, which is proportional to the momentum? Well, I have to read it off on the EK diagram now. Okay. So at this point in space, at location B, the electron will have a wave vector, which I call k sub b. Okay. Now you can go the other way around also. I can take electrons, say initially with a lot of kinetic energy. All right. And suppose I've chosen a wave vector which points in this direction. So I've chosen a wave vector or velocity pointing to the right. All right. So I'm shooting, kinetic energy is a scalar quantity, but in this case, you have to look at the velocity vector also. And velocity or wave vector, those are vector quantities. Okay? So I'm choosing a velocity vector, say, pointing to the right for electron located at location B. Okay. Now, which way is the force on that electron? To the right or to the left? We looked at the electric field, right?
It would still be to the left.
To the left.
Force.
Okay. So now what I have is I'm shooting electron uphill, right? So it's already got some starting kinetic energy, but it's moving uphill. So what happens to the velocity of the electron? It gradually slows down. Okay. So it's like rolling a marble up the hill, if you will. Okay. So if you launch ball with a certain velocity at the bottom of the hill and you roll it up, what's going to happen? It'll roll up the hill, but gradually slow down. And then when it comes to the top of the hill, where it's lost all its kinetic energy, the marble will roll back, right? So the electron will turn back. So these are sometimes called classical turning points. All right. Now, if electron was just a pure classical particle, every time once it's lost all its kinetic energy, it will turn back. But we know, of course, from chapter 2, that electrons have a wave particle duality. So we'll see later on that you can also think of this electron not just as a particle, but as a wave with a finite reflection probability, but a finite transmission probability into the gap. Does anyone remember what that transmission phenomena was called in quantum mechanics?
Quantum tunneling.
Excellent, very good. All right, so I want you guys to study this figure very, very well, okay? Because I can guarantee you in the exam, I think I've given you some homework problems, and also in the exams, I will give you problems testing your understanding of band diagrams and band structures, okay? So make sure that you understand this extremely well. Because once again, all our device analysis will be done in terms of this, mostly in terms of simplified band diagrams. Once in a while, we'll throw in these EK band structures also, all right? Now, let's go back to this EK relationship, this parabolic relationship, okay? And see a couple of other relationships based on that, okay? So first of all, let's take the time derivative of momentum. Momentum is h bar k, so dp dt can also be written as h bar dk dt. Now, from Newton's second law, dp dt equals a force, all right? But in this particular case, the force that I'm dealing with is only the external force, the force due to the batteries, for example, hooked up to the transistor or whatever, okay? Was that the only force? No. If I was to look at the crystalline structure, you'd see that at every location, I have this periodic crystalline potential, okay, 1/r type potential, and the electron is actually moving in a highly complicated potential profile, which is this 1/r type potentials, but then on top of that, I'm superimposing this overall external potential, okay? So it's a very complicated problem. But this periodic crystalline part of the potential I've solved once and for all, and I said that information can be captured in terms of the band structure or the effective mass. So I don't worry about this internal periodic potential anymore. I just worry from now on with the external part of the potential, all right? So if I was to write Newton's law from scratch, I really should have written actual momentum dt equals the total force F internal plus F external, okay? But as I've said, I've solved for the internal part of the force once, and that information is captured by m star, okay? So then on the left-hand side then, I don't have the actual momentum of the electron, but I have something which is sort of similar to the concept of the electron momentum. This is known as quasi momentum or the crystal momentum. Therefore, P or h bar k is not the actual momentum, it's the quasi momentum or the crystal momentum. And because it's a quasi momentum, on the right hand side, I don't have the total force, I just consider the external part of the force. That may have been confusing. So let me start again. So Newton's second law tells us that the time derivative of the actual momentum, P actual, equals a force. But the force can be broken down as the internal periodic crystalline forces plus any external force that I might apply because of a battery or whatever, okay? The internal forces I solved once and for all, and that information is captured in this effective mass, okay? So then I no longer consider the internal force every single time. I just focus on the external force, okay? So then, obviously, if on the right-hand side, I don't have the total force, I just have part of the forces on the crystal, on the electron, just the external part of the force. On the left-hand side, I cannot have the actual momentum also, right? For consistency's sake. So I only consider the part of the momentum which responds to the external forces. And that's why this P is not the actual momentum, it's sort of a similar concept. People call it the crystal momentum or the quasi momentum. All right. The velocity is equal to P over m star, effective mass. Okay. Now P is equal to h bar k. So that's h bar k over m star. So once again, this is the quasi momentum. Now this h bar k over m star, you can also write as 1 over h bar dE dk. How do you get that? Well, you start with this E K relationship, and if you take the derivative of that, what will I get? If I take the derivative of h bar squared k squared over 2m star, I'll get dE dk works out to h bar squared. If I take the derivative of k squared, that will give me 2k over 2m star. The 2's cancel out, okay? And then I bring one of the h bars to this side. So 1 over h bar dE dk works out to h bar k, the quasi momentum, divided by m star, okay? Now E is also equal to h bar omega. So 1 over h bar dE dk is nothing but d omega dk, which in physics you may have studied is known as the group velocity of a particle, okay, or of a wave. So this group velocity is the velocity with which these wave packets describing the electron propagate in the crystal. I know I'm throwing a lot of very difficult concepts at you. So, take time to digest it. And if you have questions, by all means, ask me next time or, during office hours or whatever. Okay. But I want you to study this very, very thoroughly. Okay. Now, where you had left off last time before the break was with this figure, which are these band structures. So once again, these are plots of electron energy. Plots of electron energy increasing upward as a function of the wave vector k, basically proportional to the momentum or the velocity of the particle. Okay. Now, in the previous figure, we saw we have parabola, but those were idealized diagrams. One finds that in a real semiconductor, you have kind of parabolic shapes, but these are distorted parabola. If you move up higher in energy, clearly you see that it doesn't quite follow the parabolic pattern. Okay. Now, we already saw also that the effective mass, it works out to h bar squared over the second derivative, which is known as a curvature. How do you get that? Well, E equals, once again, h bar squared k squared over 2m star. If I take the first derivative, dE dk, we already saw that's given by h bar squared k over m star. If I take the second derivative, the k vanishes. Okay. So then by inverting this, you can write m star, the effective mass, as h bar squared divided by the second derivative of E with respect to k, which is known as a curvature. Okay. So that tells you immediately that if you have a band structure, which has a sharp curvature, the electrons in that band will behave as if they have a low effective mass. On the other hand, if I have a curvature which is more flat, you'll have a higher effective mass. So we said before the break that if I made a transistor in gallium arsenide, in principle, those would be faster transistors because electrons in gallium arsenide are more agile than if I made a transistor in silicon because it's got a gentler curvature over here. Okay. Other funny things that we talked about was if I look at the valence band, now that's an inverted parabola, so that has the negative curvature. Therefore, electrons in the valence band have a negative effective mass. Now, that seems like a very strange concept, right? I mean, how can a mass be negative? Well, remember, once again, this is not the actual mass of the electron. This is the effective mass, which is capturing the interaction of the electron with the periodic crystalline potential. Okay, so it's just a mathematical construct, if you will. Now, there's a lot of information in these band structures that you'll study if you ever take a graduate course. Just wanted to give you a flavor of that. Okay. Now, one of the things that you'll see clearly is these parabola don't seem to be symmetric. And normally a parabola is going to be symmetric, right? But these don't quite look symmetric. And that's because I'm plotting this curve as a function of K in different directions of the crystal. What does that mean? Well, if you remember in chapter 1, we looked at the crystal structure of common semiconductors, and we saw that for silicon, gallium arsenide, et cetera, they have a face-centered cubic crystal structure where you have atoms at the corners and the face centers, and then you have the second atom at A/4, 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 et cetera, et cetera. Then we talked about the different Miller indices. So along these edges, for example, those are the 1, 0, 0 axes, for instance. Along the diagonals, those are the 1, 1, 1 directions, and so on and so forth. Remember that? Well, what I'm doing is, here I'm plotting the E as a function of K, where K is a vector pointing in different directions in the crystal. So if I point along the 1, 0, 0 axes, which are along these edges of the cube, like so or like so, that is this direction. The K equal to 0 value is denoted as the gamma point. So this Greek symbol gamma means that K equals 0. So I'm at the bottom of the parabola, K equal to 0. And then if I look at the momenta from 0 along the 1, 0, 0 directions, that's known as the X direction. Okay, so that's the 1, 0, 0 direction. On the other hand, if I plot the EK relationship along the diagonals, along the 1, 1, 1 direction, that's called the L direction. Okay, these are just notation. So when you see these diagrams and you see the symbols, that tells you in which direction I'm looking at the EK relationship. And clearly, if I'm looking at different directions of the crystal, you know, these shapes of the curves can be different, as shown over here. All right. The valence band is particularly interesting because you can clearly see it's got a very complicated structure. Okay. You have 3 branches in general. Now, let me ask you, if I look at this top figure, okay, versus the intermediate figure, which one has a sharper curvature? The topmost curve or the one in the middle?
It's kind of hard to see underneath the red. Are you
Yeah, so
referring to?
okay. So let me sketch it out. So suppose I had a curve like this and a curve like that. Curve 1, curve 2. Which one is more curvy?
Curve 2.
Curve 2. Okay. So that's why the top curve is known as the heavy hole band, and this is known as a light hole band, because in a sharper curvature means lighter effective mass. Okay. Now below that, you'll see, so and these two are at the same energy at K equal to 0 at the gamma point. Now below that, you'll see another curve. Okay. This curve is known as a split off band. And this has to do with, believe it or not, a relativistic effect in the crystal. Now, I'm sure most of you haven't taken a course in relativity, neither have I. But you know, hopefully you've read somewhere that relativity effects show up at velocities close to the speed of light. Okay, well, it turns out, although normally electrons in a solid move at far slower speeds, where you think that relativity wouldn't be important, it turns out near the nucleus, when electrons orbit right near the nucleus, where they see a very high electric field, they can travel with velocities which are not quite at the speed of light, but a significant fraction of the speed of light. Okay. And under those conditions, this orbital motion of the electron interacts with the spin of the electron. Remember, electrons also spin around the axes, and that's what gives rise to what's called spin-orbit coupling. And that then causes this third band, the valence band. Okay, that's all that I'm going to say. But if you take a graduate course, like I said, all of these will be studied in great detail, and it's got really interesting implications for semiconductor devices. So it's not just exotic physics, they all really matter. Now, one other thing that we had pointed out, let me see if you remember that. If I compare the band structures of silicon versus gallium arsenide, you notice a significant difference. That is, in silicon, the minimum of the conduction band is at a different value of K as the maximum of the valence band, while in gallium arsenide, the minimum and the maximum both occur at K equal to 0, or the gamma point. Do you remember what the significance of that statement is?
One of them has an indirect band gap and the other one doesn't. So it's like
Very-
2 steps versus 1 step.
Very good. So which one is indirect, silicon or gallium arsenide?
Silicon is indirect.
Yeah.
So it
So
has the phonon and the photon.
excellent. Okay. So in silicon, to transition from valence to conduction band, you'd have to absorb a photon, which makes vertical transitions, and a phonon. Or conversely, to emit, you have to emit a phonon and a phonon. Sorry, these horizontal movements with a lot of change of momentum are given by phonons or lattice vibrations, and vertical transitions are given by photons. Very complicated processes, and therefore they're not very effective for optoelectronic devices such as lasers or light-emitting diodes. Gallium arsenide, on the other hand, it's a direct semiconductor. It doesn't need to involve phonons. You can just absorb or emit photons, and therefore you can make lasers or LEDs very easily in gallium arsenide. Okay. One final thing, and this also will not be tested on, but if you take a graduate course, you'll study more about these. And that is, if you look at, for example, the gallium arsenide conduction band minima, the minima is over here. What you then do is you can plot what are called equi-energy surfaces. What does that mean? Well, I can choose a particular energy, say like so. Okay. And I can find out all the different k vectors where the electron has this energy. Okay. So I can plot then contours like these. These are constant energy surfaces. Okay. Plotted as a function of wave vectors along the x-axis, y-axis, z-axis. All right. I can choose another value of energy. I'll get another energy contour. Okay. So these are called equi-energy surfaces or contours. Okay. And why is that relevant? That's relevant because then you can go from one energy surface to another, and you can get these curvatures in the different directions. And what you'll find is this effective mass is not going to be a constant. It will depend on which direction in the crystal I'm looking at. So this effective mass actually becomes what's known as a tensor quantity. It's not a scalar quantity. It depends on whether I'm pointing along this axis or that axis or different axes and so on and so forth. Okay. In the case of silicon, you have 3 different directions, X, Y, Z. 2 of them have the same effective mass, which is known as a transverse effective mass. And the third direction will have a different effective mass known as a longitudinal effective mass. All right. So I want you to keep this at the back of your mind, because as we get into chapter 3, we'll introduce 2 other effective mass concepts, the so-called density of states effective mass and the conductivity effective mass, both of which will be given in terms of this effective mass in terms of the band structure. Okay. So I just want to plant that thought in the back of your mind. Once we get into the discussion, I'll revisit this again. Okay. Now, all of these things, once again, if you took graduate courses, you learn have very interesting implications for transistors or other devices. Okay. So for example, in your cell phone, you have silicon transistors which have been purposely strained. So this FCC crystal has been strained so that you maybe pull the crystal in this direction. So instead of an FCC, I may have a distorted crystal like so. This direction may be longer than these 2 directions. Okay, that strained scenario is known as strained silicon. And companies like Intel, Samsung, all these companies purposely introduce mechanical strain in the crystal. Why do they want to do that? They do that because by doing so, you can modify these effective masses. And as you just saw, if you modify the effective mass and you increase the curvature, you can make the electrons travel faster. And that's what companies like Intel and Samsung and TSMC have been doing to purposely strain the crystal, to increase the curvature of the conduction band so that the electrons travel faster. That's how you have faster transistors. So all of this may sound like, God, why is he talking about all these, weird, exotic concepts? Why do we care as engineers? They all have relevance for technology. So I find it very, very interesting that, these details of quantum mechanics have real practical ramifications. And that's all that I'm not going to go into depth because, as you can see, it's starting to get kind of complicated. And I'm not going to test you on these detailed concepts in the exams also, so you don't have to freak out. I am going to test you, however, on the basic, band diagrams and things like that. So you need to be very comfortable how to read band diagrams. But, this higher order physics, I'm not going to test you on that. Okay, that is meant to be a teaser, if you will. And hopefully you'll go to grad school and study solid state. All right, one final comment about band diagrams. In this case, I'm showing a band diagram of an alloy or something called a heterostructure. Heterostructure. What that means is I don't have the same semiconductor everywhere. I have different semiconductors in different locations. I'm showing an example of that where I'm taking a gallium arsenide layer and sandwiching that between aluminum gallium arsenide, which people in the community call AL gas. So people call it gallium arsenide gas and aluminum gallium arsenide AL gas. So, if you want to sound like an expert, that's what you should call them, not aluminum gallium arsenide, but AL gas and gas. Okay. Now, why do you want to do that? But it turns out gallium arsenide has a band gap of 1.43 electron volts. That's my conduction band. That's the valence band of gallium arsenide. On the other hand, AL gas, depending on the amount of aluminum that I have, in this case, I'm putting in 30% aluminum, 70% gallium, I have a larger band gap. More aluminum, the larger the band gap becomes. Okay. So by constructing a heterostructure like this, hetero means different semiconductors slapped together, I end up with a more complicated band diagram as shown over here, which is very interesting. So what I have is, I see that the electrons in the gallium arsenide are confined by these barriers made by the AL gas. Same thing happens in the valence band. Now, what does this remind you of? Well, this should remind you of one of the problems that we solved in chapter 2, the famous particle in a box problem in quantum mechanics. Remember that? Now, of course, what we solved was an infinite box. This is not an infinite box, it's a finite box, but the same kind of math applies. And the math that we saw was, now that I can find electrons by solving the Schrodinger equation, I have these different eigenstates and eigenenergies. I'm showing E1, you have E2, and so on and so forth. Okay. Similarly, in the holes, you have this lowest state, next state, and so on and so forth. Okay. Now, how does it matter? Well, if I had regular gallium arsenide without this heterostructure, the bands would be like so. So if I was to make lasers out of it, I could take electron in the conduction band, recombine that with a hole, and out would come a photon h nu with an energy equal to 1.43 eV. Okay. Suppose I made a laser or a light emitting diode in gallium arsenide, that's what I'd get. All right. Now, it turns out 1.43 eV corresponds to infrared photons, IR, slightly longer wavelength than red photons. And as such, you could not see that with your naked eyes. So, such a light emitting diode would be of limited use if I can't see the light, right? They're still useful. In fact, in your remote controls on your TV, you have a laser made out of gallium arsenide that you point at the TV. Because when I'm changing the channels, I don't want an irritating light bouncing around. All that I need to do is to change the channels, right? And infrared laser beam does perfectly fine. On the other hand, if I wanted to actually see the light, I need something which would be in the red, green, or blue part of the spectrum, right? And by making this heterostructure, let's see if we can do that. So what you find is, by creating this heterostructure, I've pushed the minimum energy of the electrons in gallium arsenide from EC up to E1, and similarly for the holes from EV up to EH. So now the transition has to be from E1 to EH, right? And that's clearly greater than 1.43 EV. So what you can do is you can play games like you can, making this gallium arsenide layer thinner and thinner. You can push these energies up, and so that this transition from E1 to EH might now be pushed into the visible part of the spectrum. And that's one way you could make, for example, red LEDs or red lasers and things like that. All right. So all kinds of interesting optoelectronic devices can be made. When you make these heterostructures, however, you have to be careful about lattice matching, as we discussed in chapter 1, and this is the figure that I took from there. So this shows the lattice constant, which is the size of the FCC cube in this case, and on the y-axis have the band gaps. So the gallium arsenide, aluminum gallium arsenide system is very interesting. You find that this is an almost vertical line, meaning that gallium arsenide and aluminum arsenide pretty much have the same lattice constant of 5.65 angstroms. So when you grow these heterostructures, there's not going to be any lattice strain or mismatch, which is why this is a particularly interesting crystal system to grow. On the other hand, let's look at another type of semiconductor, silicon. Let's see, where is silicon? I guess they're not showing silicon over here. Silicon would be at 5.43. So silicon would have been here, 5.43 angstrom lattice constant and 1.1 eV electron volt. Okay. Germanium, on the other hand, has a lattice constant of 5.65 and a band gap of 0.7. So germanium will be over here. Okay. So if I try to grow germanium on silicon or silicon on germanium, heterostructures like that, would there be lattice mismatch and strain or no mismatch?
There would be some strain.
Exactly. So going back to our earlier discussion, remember we said that if you strain a crystal, you can change the effective masses. And if you make the curves curvier, the effective mass would go down and the transistors would be faster. So that's exactly how they make strained silicon. And that's how you get, very high frequency gigahertz type performance in your cell phones and things like that. Okay. So hopefully you see how everything kind of fits together. All right, so that's all that I have about band diagrams and band structures. I'm going to switch gears a little bit now. I'm still in chapter 3, but now I'll start talking about carrier statistics. What does that mean? Well, we have so far talked about the fact that you're allowed energy states in the conduction band and valence band, but nothing in the energy gap. Okay, but I haven't told you how many electrons or allowed states I have in the conduction band or the valence band, right? I've just told you that there are states allowed in the conduction and valence band, but I haven't really quantified that. And I've also not told you how to calculate these numbers of electrons and holes. So that's our next order of business. All right. Any questions on the band diagrams? All right. So to answer our question about numbers of electrons in the conduction band or number of holes in the valence band, we actually have to answer 2 questions. All right. First is the number of allowed states, quantum mechanical states you have in the bands. And that's a quantity known as the density of states. If let me move to the yeah, I'll go back to the previous ones before. Okay, so here I'm showing the conduction band minima, and of course there's the top of the conduction band, valence band maxima, the valence band down below. So these are the allowed states. Okay, so as I said, you first have to figure out how many allowed states, quantum mechanical states, are allowed as the function of energy, and that is given by this function, which is known as the density of states. All right. And we'll do the calculation I'll show you the calculation in a second, and you'll find that this density of states, N of E, as a function of energy, will have a parabolic shape also. Okay, so you'll have few states as a function of energy close to the bands. As you move up in energy, you'll have more and more allowed states. All right. So the way to read this is, if I look at an energy window between, say, E and E plus delta E, small delta E, I'll have that many allowed states between those 2 energy spacings, E and E plus delta E. Okay. And as you can see, because it's a curve, the density of states itself is a function of energy. So that's the first piece of the puzzle. The second piece of the puzzle is, just because I have allowed quantum mechanical states, does not necessarily mean that I'll actually have electrons occupying those states. That information is given by the second function, which is known as the Fermi Dirac distribution function, f of e. And that's what's plotted in the third column over here, also as a function of energy. Okay. The value of this is 0 over here, and the maximum value turns out to be 1. So for example, you'll find that as you go to higher and higher energies, the probability of occupying those allowed energy states becomes smaller and smaller and smaller. Okay. As you go to lower and lower energies, the occupancy factor is going to be closer and closer to 1. And that's consistent with that, what I told you earlier. And that is that in the valence band, the states are almost completely full, while in the conduction band, the states are almost completely empty, not totally empty. Okay. So once again, therefore, the answer to the question of how many electrons I have in the conduction band will be answered in 2 parts. I'll first calculate the number of allowed states as a function of energy, and then multiply that by the occupancy factor, the likelihood of occupancy, or the average occupancy rather, which is called the Fermi Dirac distribution function, f of e. So n of e times f of e dE tells you the number of electrons between an energy E and E plus dE, okay? So if I consider 2 energies, E and E plus dE, that's how many electrons I'll have. How do I then get the total number of electrons in the band? Well, very easy. You simply integrate from the bottom of the conduction band to the top of the conduction band, which for all practical purposes can be replaced by infinity without introducing many errors, because as you go up in energy, you see that the f of e basically goes to 0. So even if I replace the higher limit instead from EC top to infinity, it doesn't really change the integral any further. So that's the integral that we'll do. Okay, so that's a big picture. Let's go back then and look at each of these terms one by one, starting with this f of e. Okay. All right. So what does this Fermi Dirac distribution function mean? Well, let's start with the classical problem, which is the so-called Maxwell-Boltzmann distribution function that hopefully you studied in physics 303K or freshman physics or whatever. Okay. So where you hopefully remember, you learned that if you have 2 different energies, E1 and E2, we know that, and suppose the energy separation is delta E, okay? You may remember that in physics, the probability of jumping from the lower energy state to the higher energy state is given by the so-called Maxwell-Boltzmann factor, e to the power minus delta E over KT, where K is the so-called Boltzmann constant. So this K is not the wave vector. K is the Boltzmann constant, and T is temperature in Kelvin, okay, degrees Kelvin. There's too many Ks. So this is Boltzmann constant, and temperature is in Kelvin, degrees Kelvin, okay? And delta E is from the ground lower lying state to the higher lying state, okay? So what this tells you is, as I go to higher and higher energies, the likelihood of exciting it from the lower level to the higher level decreases exponentially. And that's the famous Maxwell-Boltzmann distribution function. Do you remember seeing that in your physics classes? All right. Now, one thing that you may not have studied is sort of an extension to the problem, and that is at this lower energy E1, suppose I have N1 possible energy states, and at the higher energy E2, I have N2 possible energy states. Okay, so then the generalization of this Maxwell-Boltzmann term is the number of particles in the higher energy N2 divided by the number of particles N1 at the lower energy is given by the number of states N2 times e to the power minus E2 over KT over N1 times this, where these N1 and N2 are what we just called the density of states. Okay. Now, if N1 and N2 are the same, notice this would work out to, if n1 equals n2, these two then cancel out, and then n2 over n1 works out to e to the power minus e2. You bring the e1 in the numerator over kt, and e2 minus e1 is delta e. So that's your Maxwell-Boltzmann occupancy factor. Okay. Now, once quantum mechanics was developed, people realized that this classical distribution function had to be modified, because remember in chapter 2, I told you that depending on the spin of the particle, you have two classes of particles. Okay, so spin half particles, spin half, or 3 halves, 5 halves, those particles are called fermions after Enrico Fermi, while integer spin particles, integer spin like spin 0, 1, 2, etc., are called bosons after an Indian physicist, Satyen Bose. Okay. Now, in the case of fermions, the particles are subject to the Pauli exclusion principle, which tells you that, who remembers what the Pauli exclusion principle is?
No two fermions can be in the same state.
Very good. While with bosons, there's no such restriction. Okay, you can put any number of bosons at a particular state. Okay, but with fermions, you can at most put one fermion per quantum mechanical state. All right, so once that was recognized, people realized that this Maxwell-Boltzmann classical distribution function had to be modified. Okay, and the quantum mechanical distribution functions f of e, where f is the average occupancy of a level or a state at energy E. Okay, is the average occupancy of a quantum state at an energy E is given by 1 over e to the power energy minus a constant, which is called the chemical potential mu, divided by kT, where k once again is a Boltzmann constant. It's not the wave vector. T is temperature in Kelvin, plus or minus 1. Plus in the case of fermions, minus in the case of bosons. Okay. Now these distribution functions were analyzed by 2 other physicists also. So in the case of the fermions, it was Enrico Fermi and Paul Dirac who did that study. So that's why it's known as Fermi-Dirac statistics. While in the case of bosons, Boson sent his initial paper to Albert Einstein, who made dramatic improvements to the paper, and that's why it's known as Bose-Einstein statistics. Okay. So the only difference is it's +1 in the case of Fermi-Dirac statistics for fermions, spin half particles such as electrons, and -1 in the case of Bose-Einstein. That seems like a trivial difference, right? Let's see what the implications are. Well, first of all, let's look at energies E much greater than mu, the chemical potential. And if E is much, much greater than mu, e to the power that quantity is going to be a large number, right? And in that case, the plus or minus 1 doesn't really matter. So you can kind of ignore the plus or minus 1. And this then becomes approximately, so for energies much greater than mu, okay, f of e becomes approximately e to the power minus, you bring this to the numerator, minus e minus mu over kt. And notice, this is exactly like your classical Maxwell-Boltzmann distribution function. So what it tells you is, for very, very high energies, energy is much greater than this constant, which is known as the chemical potential. Classical physics is just fine. The differences with classical and quantum results show up at lower energies or low temperatures, okay? Now, what would be the difference then? Well, let's consider energies very close to mu. So then e to the power e minus mu minus over kt is going to be a small number. So then you can't ignore the plus or minus 1 in the denominator. Okay, let's see the 2 different cases. If it's -1 for bosons, what's going to happen? Well, look at E equal to mu. What's e to the power 0 equal to?
1.
equal to 1, right? If E equals mu, E minus mu is equal to 0, and E to the power 0 is 1. So then for bosons, I get 1 divided by 1 minus 1. It goes up to infinity, right? On the other hand, for fermions, I have plus 1, right? So then E to the power 0, suppose I've chosen an energy equal to this chemical potential mu. E to the power 0 is 1. So I'll get E to the power 0, which is 1 plus 1. I get 1 over 1 plus 1, or half. Okay. How about energies much lower than mu? Well, if E is less than mu, I end up getting E to the power minus a very large number, negative large number, which is practically equal to 0, right? So in the case of fermions, because I have plus 1, I end up getting 1 over something close to 0 plus 1, or approximately to 1. So therefore, for Fermi-Dirac, the maximum occupancy is 1. And that is nothing but an expression of your Pauli exclusion principle. Okay, I cannot have more than one fermion in a quantum mechanical state. At the Fermi level, at E equal to mu, this is known as your chemical potential. Okay, it's just a thermodynamic constant. For fermions, that's also known as a Fermi level. That's what we'll describe later on. The occupancy is half. While for bosons, it blows up to infinity at the chemical potential. Okay. Although we will not discuss bosons any further, that blowing up is very, very, very interesting. That's a phenomenon known as Bose-Einstein condensation, and is responsible for a whole bunch of very interesting phenomena, such as superconductivity, superfluidity, and things like that. But that's not going to be the subject of our class, so I'll not talk about bosons any further. Okay, but fermions we have to discuss. Now, sometimes in the literature, you'll hear people say that the Fermi-Dirac factor with +1 is a probability of occupying an energy state by electron. That's actually not true. This Fermi-Dirac factor is the average occupancy of a level by electron. Okay. The reason people sometimes mistakenly call it probability is because what are the ranges of probabilities? Probabilities can range between
0 and 1.
0, 1. Okay. Now, since the occupancy for fermions also ranges between 0 and 1, people will kind of sloppily call the F of E as a probability of occupying a state by electron. But that's not strictly true. It's really the average occupancy of a state by electron. Okay. Now, once you recognize that, once you become experts, I'll forgive you if you once in a while call it the probability of occupancy. And sometimes textbooks will also, sloppily call it probability, as long as you are clear in your mind that it's not really the probability of occupancy, it's the average occupancy. Okay. And it has to be the case because, certainly for bosons, you see that this F of E goes up higher than 1, right? And it cannot have probabilities higher than 1. Okay. So F of E is always the average occupancy of a state. So very, very different for low energies or low temperatures between bosons and fermions. But for high energies, they both asymptotically approach the classical Maxwell-Boltzmann distribution function. Okay, so now let's replot the F of E for Fermi-Dirac statistics for fermions, shown over here. And I'm now rewriting it as 1 over e to the power E minus, instead of mu, I'm calling that EF because the chemical potential for fermions is known as the Fermi level over KT plus 1. And let's graph it out. Okay. So I'm plotting F of E now, not as a function of E minus mu over KT. That was a normalized way of plotting it. Just replotting it directly as a function of energy. Now let's see what the values would be. Well, we've already seen that for energies equal to the Fermi level, I get 1 over e to the power 0, which is 1 plus 1. So I get half. For energies much greater than EF, high energies, I can kind of ignore the 1 over here, and it kind of exponentially gives you e to the power. You bring this to the numerator, so it's e to the power EF minus E over KT, or you get this Maxwell-Boltzmann type classical e to the power minus energy over kT type function. On the other hand, if energies are much less than EF, yeah, I get e to the power a large negative number. E to the power minus infinity is 0. So I get f of e equal to 1 over 0 plus 1. So it asymptotes to 1. Okay. Now we are also plotting this now as a function of temperature. Now let's see if temperature was very low, say 0 Kelvin. What's going to happen? The function will be a step function as shown by this blue curve over here. Why? Because then if t is equal to 0, for energies just slightly above EF, I get e to the power a positive number divided by 0, or a large positive number, e to the power infinity, which gives you infinity. So it drops to 0. While if e is slightly less than EF, it's a negative number divided by 0. So I get e to the power minus infinity, which is 0. So boom, it goes to 1. Okay. So what it tells you is at very low temperatures, say at absolute 0, the highest occupied energy level in a semiconductor or a metal is a Fermi level. That is sometimes also known as a Fermi surface. Fermi surface. Okay. So you can think of it, if you plot energy as a function of wave vector, say kx, ky, kz, as I was plotting a few minutes earlier, you can only have states occupied up to the highest occupied k value of the Fermi wave vector, and this energy is known as your Fermi surface. Okay. Now let's see what happens as temperature increases. As T goes up, you'll find that the step function becomes more and more rounded. So basically, I take some electrons from below the Fermi surface of the Fermi sea, and I can excite them to higher lying states. And in the process, I can create holes and conduction electrons. Okay. The more higher the temperature, the function gets more and more rounded. But in each case, at E equal to EF, the value goes through half. So you can think of the Fermi level as A, the highest occupied energy level at very low temperatures, or the energy level with the average occupancy is going to be half regardless of the temperature. Okay. This is the Fermi-Dirac occupancy factor for electrons. How about for holes? Well, if a state is occupied by an electron, it's clearly not occupied by a hole, and vice versa. And therefore, you can write down the whole distribution function as simply 1 minus f of e. And if you do the math, if you take 1 minus this quantity over here, you'll find that it's a very similar looking expression, except that the symbols get flipped. So instead of e minus ef, you end up getting ef minus e over kt plus 1. And if you had to graph it out, 1 minus f of e for holes would be the mirror image of this. It'd be like this, because 1 minus 1 over here asymptotes to 0, and 1 minus 0 over here asymptotes to 1. And at the Fermi level, 1 minus half will give you half. Okay. So that's the occupancy factor for holes. And that's the occupancy factor for electrons. Okay. All right. So the next step is figuring out this integral, because I want to calculate the total number of electrons in the conduction band or the total number of holes in the valence band. And as I said, you answer that in 2 parts. I've already answered the first part, which is the average occupancy of the states. I now have to answer the second part, which is how many states are there as a function of energy, the so-called density of states. And once again, the density of states, N of E times dE, is the number of allowed states between an energy E and E plus delta E. Okay, so that's what the density of states means. All right. Now, how do you calculate that? Well, it turns out you can calculate that by counting states, as we did in the case of the particle in a box problem. So just to remind you, it's a funny kind of box. If you had a particle in a box, we saw that we have, say, the first allowed state E1, then the next state E2, and so on and so forth, right? So E1 was given by h bar squared K1 square, okay, where K1 corresponds to half of a wavelength, right? H bar square K1 square over 2m star. Now, what's K1 equal to? Well, K1 equals 2 pi over lambda 1. Now, lambda 1 is twice the length of the box, right? Because that's half of a wavelength. So lambda 1 equals 2L. So this is what we discussed when you looked at the particle in a box problem, right? So K1 squared will be 2 pi over 2L. That's lambda 1 squared. So that's H squared K1 squared. K1 is 2 pi over 2L over 2M, right? The next state was a full wavelength. So lambda 2 was equal to the length of the box, right? So the next energy state would be H bar squared over 2M, 2 pi over L squared. So what we saw in the particle in a box state was the energy En was proportional to N squared, where N equals 1, 2, and so on and so forth. Do you remember that? So that's how you count states. Now, what is the box that I'm talking about? Well, the box is, if I have a crystal of length L, now within the crystal, you have this periodic crystalline potential that you talked about, okay? The box that I'm talking about is the length of the crystal. So you can think of this as a box, and then outside of that is the vacuum, okay? So depending on the length of the crystal, I have different values of these allowed wave vectors, and I can count the allowed quantum mechanical states. So I first count states as a function of wave vector k, all right? I'm not going to go through the details of the calculation. This calculation of the density of states and the calculation of the Fermi-Dirac distribution function are both given in the appendices, okay? So if you're interested, in fact, I strongly urge you to try to read through those derivations, okay? Even though I'm not going to test you on either of them in the exams, all right? All that you need is a final answer, but it's nice to know where the expressions come from, okay? So the way you calculate the density of states is you first count states as a function of wave vector k, okay? And as shown in one of the appendices, you end up getting in 3 dimensions a result like this. It's given by the spacing in k space, delta k, corresponding to the spacing in energy, times L squared over 2 pi cubed, and then you get a factor of 2 due to spin degeneracy, okay? I'm just stating this. The derivation is given in the appendix, okay? Once I calculate allowed states as a function of k, you then have to convert that to allowed states as a function of energy by making use of the band structure. Now, for most semiconductors, we have a roughly parabolic band structure. So you basically can do a change of variables, counting states as a function of wave vector k, using this relationship to convert that to states as a function of energy. And why do I want to do that? I want to do that because the occupancy factors, F of E, are a function of energy. They don't depend explicitly on k, they depend directly on energy, and through energy, they depend indirectly on k, okay? So that's why you first count states as a function of k space, all right? Because there you'll find that it's a nice equispaced distribution of quantum states in k space, but then ultimately convert that using a change of variables, counting states as a function of energy, because that's what I want to get this final integral, okay? So if you did that calculation in 3 dimensions, as described in the appendix, we find that the density of states is also a parabolic curve. Okay, so you'll get N of E will be E minus EC square root of that. Now, why is that a parabolic curve? Well, we know that the formula of a parabola is y equal to x squared, but you can turn this around and you can just as well write x equals square root of y, right? So N of E equal to square root of E minus EC is also shape of a parabola, and that's what I have in this middle row over here, middle column over here. Okay. I did not derive any of these expressions over here. I just hopefully gave you a sense of where they come from. If you're interested in the derivations, and I strongly urge you, please try to read through the two appendices, even though you'll not be responsible for either of these derivations in the exams. Okay. Now, once I have these two pieces of the puzzle, the number of allowed states as a function of energy times the average occupancy of the states, you take the product and then integrate from the bottom of the conduction band to top of the conduction band, which for all practical purposes, I can replace by infinity, and that'll give you the total number of electrons in the conduction band. And that's shown in the final column over here. So as you can see, in the band gap, I have no allowed states and therefore no electrons. As I go up in energy, I have more and more allowed states, and the number of allowed states, number of electrons goes up. Okay. But as you go to even higher energy, although I have more and more allowed states, the average occupancy of those starts going down exponentially, and therefore it goes to a peak and then dies down. Now, what is this value of n? It's simply the area under that curve. Okay. How about for the holes? Well, I have to multiply the density of states in the valence band times, do I multiply that by f of e, or should I multiply that by something else?
Can you repeat your question?
For the holes in the valence band, I similarly have to multiply by the density of states in the valence band, as shown by this curve. But the question is, do I multiply the density of states in the valence band by f of e, or should I multiply by something else for the holes?
It's 1 minus f of e.
Excellent. So for the holes, you multiply by 1 minus f of e. Okay. And similarly, you'll get a curve which is 0 within the gap because there's no states allowed. As I go down in energy or increase in hole energy, more and more allowed states, but then the occupancy by hole starts going down, and I get this. And if I integrate the area under the curve, I'll get the total number of holes. All right. So next week, we'll write down the expressions for these. The math looks horrible. Once again, you'll not be responsible for any of this math. You'll only be responsible for the final results. And that's all that you'll need to do the calculations. But I want to quickly go through these integrals. So that's the density of states times the occupancy factor. If you do these integrals, very, very complicated, ugly looking integrals, but the final results are very compact and nice. And that's what we'll be writing. We'll write it as a so-called effective density of states times the occupancy factor at EC, or similar expressions for the valence band. All right, so talk to you next week.